Good morning. Welcome to Krishna's class. Next, what we take up is the well-known Urysohn's lemma. We also give a proof of this appears as a tool in the proof of the Riesz representation theorem. It's a very general, nice result which we shall first explore. Before that, we introduce some notations which are useful for our purpose. Let X be a locally compact house of space. Now we denote by K compact. So K is a compact subset of X. Now we use this notation. We write where F belongs to CCX, which means a continuous function defined on X with compact support. So this and we have 0 less than or equal to fx 1. For every x belonging to x, and so this is the meaning of this notation. This notation, let me just display it. We shall be using this. It's much more handy to use this notation to write to express, to state the theorem and later develop the proof of it. Similarly, let be an open set. Okay, so what does this statement mean? Let us look at the previous statement. This statement means that is K with this notation F. This relation means F is a continuous function, in fact real valued function with compact support on X, and the X F takes values between 0 and 1, and Fx is identically equal to 1 on K. So it means the following. So let me draw a picture. So this is X. Now this is K. So from here to, see, we define a map from, from here to 0, 1. F has compact support. What does it mean? It means, see, what this theorem says is that on K, the function takes the value 1. Okay? It's a continuous function which takes values between 0 and 1. And further, you have this property that it's having compact support. So it means there is some compact set. Say, you can write say K tilde. K tilde is compact, so that the support of the function is non-zero only here. Outside that, the function takes the value 0. So that's the meaning of that. So on K, the function takes the value 1, and the support of F is K tilde, that is, it has a compact support. That means the set on which Fx is not equal to 0, and to take the closure of that. So that's given by a compact set K tilde, and outside that the function takes the value 0, and the function it's continuous, it takes values between 0 and 1. Or I'll put it more clearly. See, let us take in a sort of function on R. So let us take K to be an interval AB. So you know that, let K be, you know that this is closed and bounded, so it's on R. So this is compact. Now what the theorem says is that you have a function whose graph is this. Now this is the value 1. So it takes the value 1 here, maybe even outside possibly, no problem. But there is another set, bounded set, CD, and then a say C prime, D prime, or some bounded, okay, some compact set contained in this, so that the function takes the value something like this, not necessarily monotonically increasing or decreasing, but see, it could even be like this. Okay? Doesn't matter. But what matters is this: the function takes the value 1 here, between, when on the set, so x is equal to r here. On r, the function takes values between 0 and 1, and over this part, that is on the interval AB, it takes the value 1, and then it has a compact support, some compact set on which the function lives actually. Okay? And what you have is outside, this function is identically 0. So I have taken a interval, an open interval, and outside which certainly it is 0, and even inside it is 0. But the closure of the set where the function takes non-zero values is compact. So that's the meaning of it. Now let us take the next part of the notation, we use this notation. So V is an open set. We are giving a meaning to this. Okay. This says F belongs to continuous function less than or equal to 1. Those two conditions are already there. Support of F is contained in. Okay. So this is the meaning of this statement. Now that's obvious. So what it says is that, see, in this situation, see, we take V as CD, the interval CD. It need not be an interval at this time, but we are probably making it more visible and simple. So this is an open set, and K is, and what we mean by this notation is that there is a continuous function with compact support on X here R, and 0 less than F less than or equal to 1, and this is for every X, and support of F is contained in. Okay, then you use this notation. Now what we shall do is combine these two notations. So we write to mean the following. This means the following. So here K is compact, V is open, and K is contained in V, F belonging to BC X. It's a continuous function with compact support X with 0 F takes values between 0 and 1, and F is identically equal to 1 on K. Now this takes care of this part. The portion, some aspects of this part also has been written already, and all that you need is and support of F is contained. Okay, so let us just give a diagram to possibly clarify the points and the notation. So what we have is the following. So we have, this is X, locally compact Hausdorff space. Then you have a compact set, okay, which is enclosed inside an open set. Okay. Now to remind you that it's an open set, just put this. The dotted lines or broken line the boundary. Okay. Now whereas this is compact. So V is open. And then you have F, which is continuous, less than or equal to 1. And then what more you have? F is identically equal to 1 here. And the support of F contained in the open set. Okay. And F is of course a continuous function with compact support with this form. Such a function is what is designated by this. So all these facts are squeezed into this single. Okay. Now that makes it very handy to state the Urysohn's lemma. So we'll now go to the statement of it's often said it's a lemma because it is some supporting. It's actually its major role is as supporting. Okay. So the statement of the theorem is this. Suppose X is a locally compact Hausdorff V opening X, K contained in V, K contained in V, and then K compact. That's the next. Sorry. Compact. Then there exists an F belonging to CCX such that this property is that. So this is the statement of the theorem. Now you see we could very economically write the statement of the theorem with all those notations that we have introduced. Now this means F is a CCX function, K is contained in V, K is compact, V is open, and F is equal to 1 on K, and the support of F is contained in V, and F lies between 0 and 1, takes value between 0 and 1. It's a non-negative function which is bounded by 1. Okay. So such a function exists. Now, the proof of this in general requires some notations. Now, before that, we will, okay, so we will just make a remark on this theorem. Now this shows that there exists a continuous function with compact support such that, in fact, this notation tells it's a continuous function. I am just have deliberately written it to try the point that it's a continuous function that you are talking about. The characteristic function of k is less than or equal to f less than or equal to characteristic. So this is another way in which you can express this result. Now we recall some of the results that we use. See, with X house law, K compact and V open in X, V open in X, K contained in V, we have already proved the following theorem. There exists an open set U such that, or we can use V1. We would use this indexing. V1 open set V1 such that K is contained in the open set V1, which is obviously contained in V1 closure and is contained in. Now this we have proved. In fact, that means you can have another open set with this property. Now let me see what exactly it is. We'll try to understand this statement. Now this we have already. So the repeated use of this result would come in the proof of the theorem. It is slightly longish and bit complicated with statements, so we will postpone the proof of this theorem the next lecture, but we'll prepare the ground for this result. So this is this scenario that X is there, then you have K is here, now you have V here. Now what the theorem says is this. See, there exists an open set V1 that contains K, and V1 closure. I'll just put the line. It's not. This is a schematic diagram. This is V1 closure. V1 closure is obviously So you see what the result says is that there exists an open set V1 such that V1 closure is compact. Okay, this is a V1 closure is a compact set. So K is contained in V1, is contained in V1 closure, but V1 closure is contained in V. Okay, so K is contained in V1. It's an open set. It's contained in V1 closure, and this is compact. This is open, and V1 closure, and V1 closure is contained in V, the given open set, and this is of course this is again open. This we have already proved. Okay. So given K and the open set V, in between you can bring in an open set whose closure is compact and such that it is contained inside V. Now we will be using this result repeatedly because you see that the situation where it can be repeatedly used, because this is compact now. Forget about K now. This is compact, and you see that this compact set is contained in V. Once again, you can interpose something. You can have a V2 taking up the same property, namely V1 closure is contained in V2. V2 is open. V2 closure is compact, and V2 is contained in. So this kind of results, this repeatedly you can apply this, and this is crucial in the proof of the theorem. Now let us see how we are going to prove this result, or what we expect. Just give a visual, more, clear picture of this result. Let us take up the situation. Now, the first one for this purpose, you see that let x be equal to 1, k be equal to interval a, which is closed and bounded interval. So this is compact. Being a closed bounded interval of R is of course a locally compact Hausdorff space. Now you see that this is the interval AB. This is compact. This is the compact set. Not all compact sets are closed and bounded intervals, but all closed and bounded intervals are compact sets. So that now what you can do is you can find a C and a D such that C is less than A, D is greater than B, such that open. In fact, there are several choices for C. But if you just take A minus epsilon and B plus epsilon, that serves the purpose. No matter how small epsilon is, as long as it is positive. Okay. Now, what is this theorem says CD. AB is contained in CD. Now you take CD closure. This is equal to you include the endpoints also, or what are called the endpoints also. We then take the closure of that. And you see that AB is which is compact, which is contained in that. Okay. Or in between, if you have an open set, then of course that also is there. Right? Now one can choose. So note that for any epsilon positive, A minus epsilon, A plus epsilon, that is B plus epsilon, satisfies the conditions B1. Okay, this is an open set. And if you take the closure, what is the closure? The closure is A minus epsilon to B plus epsilon. So you see, there is plenty of sets of this kind. In fact, you see that you can keep on having this, then this is A minus epsilon, this is B plus epsilon, and then you see once again you can repeat the same thing because you have a compact set. Now for the compact set A minus epsilon to B plus epsilon and CD which is open, in between you can squeeze in a open set and whose closure is compact. So this is the repeated way in which we are going to use this theorem. Okay, another discussion is further. What does this Urysohn's lemma? In this simplified scenario, what is this? Saying the situation of so what do you have? This is the background. V equal to ED such that A minus epsilon C is less than A minus epsilon less than b plus epsilon less than, this is always such an epsilon exists. Okay, in fact, several epsilons do exist in this case. Then choose V1 to be option. Then you have the situation. The first statement, this is clear. K is contained in V1, contained in V1 closure, which is compact, and this is contained in V. So this is something that you have. Now what more you have? I want for a compact, a function which is bounded by a non-negative function which is bounded by 1. Okay, having compact support on R. How does the situation look like? Let us take the simple scenario. See, what it says is this. Okay. Now you see, let us draw the graph of such that okay. So this is your K. E. Then let us take A minus epsilon B plus, and then you have E. So this is K, this is B, and B closure is B plus. Now what the theorem says is, now I am drawing the graph of F. What the theorem says is, there exists an F belonging to CCX such that F is identically equal to 1 on AB. Okay, and F equal to on complement and complement, and F is therefore you are assured that F has compact support. Okay, the support of F is contained in B plus epsilon. How does this function look like? Function looks like following. The function is, see, this is 1. The graph of the function is 1 here, and it may slightly exceed, but not beyond this, because on this part the function has to be identically 0. And in between, what it says is that you can patch it up. No matter how small your epsilon is, and just see, you can actually patch it up like this. there exists such a function. Now, as long as there is a gap between a minus epsilon to a and b to b plus epsilon, see, you can draw a line from here to here, which takes the value 0 over at a minus epsilon, 1 at a, and 1 at b, and 0 at b minus epsilon. In between, it's a straight line segment. Such a function exists. Now, what I wanted to highlight in my previous diagram was that this need not be a straight line. There are several functions of this kind. But what you need is a positive gap or a epsilon positive. Otherwise, you won't get a gap to descend. Okay. Otherwise, the descent from 1 to 0 will be abrupt, and that will lead to a discontinuity at A, and also a discontinuity at, or in other words, you are having chi AB is there, so it will be 0 everywhere here. But that is not the function f that we are asking, and this is a discontinuity. What you do is you take chi AB and then you take an identically 0 function from minus infinity to a minus epsilon and from b plus epsilon to infinity, and in between you connect the graph, the bits of the graph, by straight line segments. Now this is the scenario that you have in a very simple elementary situation. Okay, so you understood the meaning of the problem. So essentially the general statement means the following. So you have x here, you have k here, which is compact, and then you have a V1 here, such that V1 closure is compact, and here the function necessarily takes the value 1, and outside V1 or outside V1 the function takes the value 0, but in between so here f is identically 1 and f is equal to 0. So the support of, see, in this case, what is the support of the function? The way in which we have drawn it, the support of the function f is equal to here it is going to be V1. So generally it is going to be now this is the content of Urysohn's lemma. Now what we try to do is to prove this theorem in a general scenario, assuming that X is a locally compact Hausdorff space and V is an open set, K is a compact set, K is contained in V, and then show that there exists F belonging to CC X such that F lies between 0 and 1, it's a continuous function, and support of F lies inside V, whereas on K the function takes the value 1. Now this is the theorem. It's a very useful theorem. Later we shall see how it gets applied, or you will need From here, a application, a form in which we want to actually apply this theorem will be a new result will be developed using Urysohn's lemma. But I think the proof, I think you got an idea of what Urysohn's lemma is all about. Our next talk, that is tomorrow, will prove this theorem in the abstract scenario. Okay, so thank you very much.